Last time we started looking at section 3.5, which is about rational functions and inequalities. And we addressed a couple of things in particular that we hadn't talked about before. Domain was something we had talked about before, actually, and so that was kind of a little bit of review. We saw a couple of things that maybe looked a little bit different in terms of how to write things or whatever, but this was mostly things that we've addressed before. But asymptotes were something we hadn't addressed before. We talked about vertical asymptotes, and vertical asymptotes are when your denominator is set equal to 0. Doesn't matter if it's reduced or anything like that for domain, but it does for vertical asymptotes. So when we look at vertical asymptotes, we have to make sure that the function is in a reduced form before we have a vertical asymptote claim. And then the second one was horizontal asymptotes, and we talked about how this was all dependent upon the degree of the polynomials. So if the degree on top is bigger, there's no horizontal asymptote, but I sort of alluded to the fact that there will be something else we need to address, and we'll do that today. If the degree on the top is less, then you have a horizontal asymptote at y equals 0. And if the degree are the same, like a power of 2 on the top and bottom, and that's your highest degree, then you look at the leading coefficients and you make a fraction out of them. We had done one example, and we'd graphed a third of it, if you will. So we'd graphed the left-hand side of this particular one, and the reason we knew we could do that is because we found intercepts. And the y-intercept crossed above the x-axis, and we talked about how asymptotes are curves that but lines that we get really close to and we don't touch. And I can't remember if I said it in this class or not, but that's almost a statement that's sometimes not quite true, but it's true most of the time. That's not a very good thing to say. But there are some exceptions, but they're few and far between, okay? For the most part, there are lines we get close to and don't touch. Now, there are two more parts of this graph that we have to do, and the reason I know there are two is because these vertical asymptotes split the graph into 3 separate sections. One section comes before x equals 2. One is between the two of them. It's between x equal 2 and x equal 3. And the other one is after the x equal 3. So there will be 3 distinctly different pieces of this graph, and we've graphed one of them. So at this point, we don't have anything else that we specifically have to test. So we get to choose. We can test any value in between 2 and 3. And any value after 3, and that will give us the sketch that we need to make for the other 2 pieces. So let's pick a value between 2 and 3. Anyone have a suggestion?
2.5.
2.5 is a fantastic value. So we're going to test 2.5. You're welcome to grab your calculator and plug it in. I don't know that we really want to plug in decimals into this messiness by ourselves. So if you plug in 2.5 and you square it, minus 5 times 2.5, and then plus 6. And then that's the denominator. So then do 1 divided by that. What do you get as a decimal, because that's the easiest for us in terms of graphing to think about? What's the decimal that you get that goes along with the 2.5? Tyler's trying to do it in his head. That's awesome. I'm not going to. Andre's got the calculator going. That's what I would do. What is it? On the bottom or the whole thing?
I was just kidding.
You're just guessing. Not really sure.
No, I have no idea.
Do you have a value for us, Andre? Almost done. Fantastic.
Yeah.
It is Friday.
I'm sorry, I'm late.
Okay. You got -4 on the bottom or for the whole thing?
The whole thing.
The whole thing you got -4. Did anyone else plug that in at the same time? Can help us double check to make sure that you got the same thing. All right, we're going to go with Andre's solution. It's -4. I don't even know. Let me see. I probably graphed it. Yeah, that's what I have written down too. So very well done. Okay, it's -4. All right, so x equals 2.5. Y equals -4. So I need 1, 2, 3, 4 down here, and I need this particular point here. That's the point that I just got. Now, again, the whole point of the point is that I need to get close to these vertical lines. There's 2 options. It's either going to look like a trapped parabola, sort of like a parabola, stuck between things, which isn't a parabola at all, but it looks kind of like it's a U shape. It's either going up or going down. Which one does it have to be here? Has to be down. Who said down? Okay, Graceland, why does it have to be down? You're right.
Because it can't touch any of the asymptotes.
Right. It can't go up because then it would cross the x-axis, which would, number 1, be touching asymptotes, and number 2, we tried to find x-intercepts last time, and we said there weren't any. So we know that it doesn't cross the x-axis. So this one would have to sort of open downward. And it would look, and it has to get really close to the edges, which is how I know it sort of looks like that U shape. Okay? So that one point determined all of it, right? That's it, just that one point. Now we need a point that's after x equals 3. What would you like to test? 4 would be fantastic. So let's test 4. I can't confirm nor deny that this is going to be the right value because I didn't test 4, I tested something else. So it would be good if a couple people would put the number 4 into this equation for us and tell us what you get. You got 2. Anybody else try? Two? All right. We've got 2 votes for 2, so we're going to go with it. So this would be over here at 4, and this would be the value 2, like this. What will this tell us that the graph looks like now?
Would it be like the one on the left?
It will. It'll look very similar to the one on the left, right? But a mirror image. It's got to get close to the line x equals 3. In order to do that, it would have to be doing this, right? And it's got to get close to the line y equals 0, the x-axis. And in order to do that, it would have to look like this. And this would be a pretty good sketch for what's going on with this graph.
Funny looking graph.
It is a funny looking graph, yeah. All right, let's try another one. We'll start from scratch on this one since we didn't have to on the last one, since we did last time. All right, asymptotes, intercepts, right? And in order to do asymptotes, we have to actually make sure that this is in simplified form. You could look at the numerator and say it's not quite in simplified form, and if you wanted to test it, what would you do to factor the numerator? You could take the 2 out because the 2 and the 4 are both even. So sort of the most you could do to look for reducing possibilities is this. And you notice that the x minus 1 on bottom is not the same as the x plus 2 on top, so it doesn't reduce. Make sense? Okay. So at this point, we're able to look at asymptotes, and vertical asymptote is the one that we typically start with. Looking at vertical asymptotes means doing what?
Solving the denominator.
Right, setting the denominator equal to 0 and solving. So I've got x minus 1 equals 0, so what is the vertical asymptote? Yeah, x equals 1, right? X equals 1. And I did this last time, and I think that it kind of helps us to gain perspective if we graph as we go. So I'm going to graph as we go. We're going to draw a line at x equal 1. And it's a dotted line because it's an asymptote. So that's approximately what we have. This is at 1. All right, we'll get some perspective there. All right, that's our vertical asymptote. Let's do horizontal now. What can you tell me about the horizontal asymptote for this? What do we look for first? Degrees. We look for degrees. What's the degree on the numerator? 1, because that's the exponent on x is 1. What's the degree in the denominator? 1. So these degrees are equal. So what do we do when the degrees are equal in the numerator and denominator? Yeah, ratio of the leading coefficients. So the leading coefficients here are 2 and whatever's going on in front of that x, which looks an awful lot like, well, there's really nothing written there. So it's an understood 1. So this ratio would be 2 over 1, or just y equal 2. So remember, x equals is a vertical line, y equals is a horizontal line. So that's why we've got that horizontal asymptote having that form. So we're at y equal to 2, and we will draw a horizontal line. This graph is going to look simpler than the last one because there's really only 2 asymptotes, right? The last one had 3, which made it 3 distinct parts. On this one, we're only going to have 2 parts. We're going to have the left-hand side, yeah, before x equal 1, and we're going to have the right-hand side after x equal 1. So we won't have as much going on this graph. Intercepts are next, x's and y's intercepts. So we usually start with x-intercepts, although the order of these things does not really matter. X-intercept means letting y equal 0. And we had a kind of a weird one last time when we did that, but check this out. If I set y equal to 0 on this, what happens to the denominator? Like if I try to cross multiply. It goes away, right? The denominator really does not affect this at all. If I cross multiply like that, I will end up still getting a 0 on the left, and I will get the 2x plus 4, just the numerator on the right. Agreed? So the denominator has nothing to do with intercepts. All right, it doesn't help us to identify them anyway. And I can solve this equation right here, right? What will x equal if I solve this equation? -2. Right, we can move the 4 to the other side. That'd be -4. Divide by 2 gives me -2. So this right here is the x value of the intercept. So my x-intercept is -2, 0. Remember, intercepts are ordered pairs. They're points. And I can plot that now. That is a part of my graph. -2 and 0. That's right here. That's the x-intercept. Now, y-intercepts are found similarly. That is to say, if the x-intercept is when y equals 0, the y-intercept is when x equals 0. So if I were to plug in x equals 0 into this equation, what would I get? -4. I'd get a 4 on top. I'd get a -1 on bottom. So this intercept has a y value that's -4. Whoops, I left off a negative. So x is 0, y is -4. That's the ordered pair that I'd need. And I can plot that. That is really not to scale. Let's try that again. All right. Okay. Oh, I think it erased my point when I did that. Oh, and maybe I didn't actually fill it in yet. I think that's what it was. All right, those are 2 points actually that are before x equal 1. They're both points on the left-hand side of the graph, correct? I have to connect them. So the only way that makes sense to do so in a smooth way would look something like this. And that gives you a lot of help on actually finishing the graph on the left-hand side. That along with the asymptotes, remember you're supposed to be getting close to them and not touching. So if we do that, this one will continue downward, getting close to x equal 1, and this one will continue upward, getting close to y equal to 2. That's terribly looking. Yours, I'm sure, looks much better than mine. No? Tim says no. All right. But you have the right idea on the left-hand side, correct? Yeah. Over on the right-hand side of the graph, we need an additional point to test. Somebody give me a value for x that we could test on the right-hand side of this graph. 2. 2 would be great. So let's plug in 2 into this equation. All right. 2 times 2 plus 4 gives me what on top? An 8, and on bottom, I have actually 2 minus 1, which is very nice. So this would be the value 8, right? 2, 8. Now, my graph is terribly awful in the sense that my scale is all funky at this point, but somewhere up here in the middle of, high ground is 8. It's high up compared to where I am, and I have x equal to 2, so we're something like this. This is a terrible graph. I will do much better when I teach it the second time around in an hour and a half, okay? All right, so as we look at this, we might want to extend the asymptote just to make sense of the graph further up. But we're going to be going through that point. And again, we don't really have any choices. We have to get close to x equal 1, and we have to get close to y equal 2. Those are our asymptotes. So in order to do that, it's going to have to look like that on the left, the left-hand side of this piece. And it has to come down and look like this on the right. Got to get close to the asymptotes. If I zoomed out and it made the whole thing look smaller, the graph would look cleaner, right? One word of caution for those of you who do have graphing calculators. You're welcome to check these as always with your calculator. I have no problem with that. Do be aware that your calculator does weird things sometimes, some of them, depending on how old the calculator is, with asymptotes. Sometimes it will try to connect dots that aren't supposed to be connected. For example, your calculator might, it's a might, but it might try to connect this fact that this goes down to infinity and the part that goes up to infinity and connect these lines, these portions of the graph with a line. And it looks like that the line is part of the graph when it really isn't. Okay, those dotted lines are not part of our graph, right? They're just reference points for us. So when your calculator tries to connect them, it's doing something that's actually wrong. Your calculator's not always right. Just be careful when you're graphing and you're like, wait a minute, that's not what I have. It may be wrong. All right, let's try another one. Find all asymptotes and intercepts, sketch the graph, same directions. All right, so let's start with vertical asymptotes. Actually, with our vertical asymptotes, we know that we have to see if we can simplify anything. We know we're not going to be able to simplify anything on this one because the x in the denominator doesn't have any way of simplifying with the x squared minus 1 in the numerator. Remember, you don't simplify terms, you simplify factors. And while the numerator does factor, what are the factors of the numerator? Yeah, it's a difference of squares, x minus 1, x plus 1, but neither of those factors is the same as x. So it won't simplify, which means what is my vertical asymptote for this one? It will. It'll be x equals 0. Okay, so on a graph, what is the line x equals 0? It's the y-axis, yes. So I've got this vertical asymptote. Good. Let's look at horizontal asymptotes now. What do you see happening on horizontal asymptotes? What do you see? The degree on top is bigger, right? The degree on top is 2, the degree on bottom is 1. So there's no horizontal asymptote. But here's where there's a catch that I haven't told you about before. If you've taken a course like this, maybe in high school, you might have talked about something called a slant asymptote or an oblique asymptote. When there is the degree on top exactly 1 bigger than the degree on bottom, you have a slant asymptote. Okay, so how do I find that information? Well, you use either synthetic or long division. So we've done synthetic division in class, so I'm going to show you with synthetic division, since that's mostly what we've done. If you were to use synthetic division and you were to divide the numerator in synthetic division, you'd have 1, 0, and negative 1, right, for the x squared, x, and the constant column. And you'd be dividing by what's in the denominator, and the denominator is a really weird one. It just says x. But we know that the x value equals 0 makes the whole denominator equal 0. So although it feels really awkward to do it, we are putting a 0 as our divisor number on the outside of synthetic division. We're not dividing by 0. Please do not misunderstand. We're dividing by x. We are dividing by x. But the number when x equals 0 is x equals 0 for that factor. So we're going to put a 0 on the outside. It's beautiful to put a 0 on the outside because it just zeroes everything out every time we do it. So watch this. We're going to bring the 1 down just like we'd done in the last section for synthetic division. And then whatever we brought down, our 1, gets multiplied by 0, which gives me, well, 0. And 0 plus 0 is 0, and then I've got the 0 there times the 0 on the outside. That's another 0, lots of zeros all over the place. And then I have negative 1 here. This piece right here is the important part. The remainder does not matter for slant asymptotes. The remainder won't be 0, okay? It won't be. Otherwise, you wouldn't have a slant asymptote, so nothing would have happened out quite like it already has. But the part that I just boxed in is the part that matters. Now, this is what we called the quotient before. What would the polynomial related to the 1 and the 0 here be? What would this factor be here?
X squared plus x.
Close. It'll have an x. Remember, oh, you know what? Let me do this because I'm out of space. Remember when we do our division, we decrease the powers. So this is the x column down here, and this is the number column, and this is my remainder, okay, that doesn't matter for the purposes of our argument today. It's just the first 2 pieces. So the first one would be x, and the second one's number is 0, so this is actually the factor x plus 0. Not a very exciting factor. But it is the factor that would come out of this if I did synthetic division. So what does that mean? Well, it means the equation y equals x plus 0, or more simply just y equal x, is an asymptote. It's not a vertical one, and it's not a horizontal one. It's slanted. It's diagonal. And you guys know what the equation looks like for y equal x. All right, we've graphed lots of lines, and that's one of the ones that you very first learned to graph. The equation for y equal x, if you plugged in numbers, right, if x is 1, y is 1, if x is negative 2, y is negative 2. This graph, or this equation, looks like this. So this is the line, y equal x. This is the line, x equals 0. Those are my two asymptotes here. Okay, if I have a horizontal asymptote, I never have slant asymptotes. Okay, but you can have vertical asymptotes with slant asymptotes. In fact, you often do. Okay, so those are my asymptotes. And then I need intercepts, my x-intercept and my y-intercept. So the x-intercept is when y equals 0, right? So if I set y equal to 0, what would this become when I cross multiply?
0 equals x.
Right, 0 equals just the numerator, right? It always boils down to being just the numerator. And you know when that value equals 0, either because you can see we factored it, right? X plus 1, x minus 1. Or if you want to do it with square roots, you can move the 1 to the other side and take the square root. It's another way of thinking about it. But when you take a square root, you put on a plus or minus. So this is x equals plus and minus 1. What does that mean? Well, it means there's two x-intercepts. There's one at 1, 0, and there's one at negative 1, 0. That can happen. We can have two x-intercepts. They're right here and here. What's going to happen if we try to find a y-intercept, that is, if we let x equal 0? There isn't any, right? There's a couple of ways you can think about that. Number one, you can think about that because you know you already have an asymptote there. Yeah? So you're not going to have an intercept. If you don't think about that, you didn't notice it or recognize it right off the bat, and you just try to plug in 0, what would happen in this equation if you plugged in 0 for x? Your denominator would be 0, right? And your denominator equaling 0 is not allowed. It's undefined. It can't divide by 0. It's not a defined operation. So I don't have any y-intercepts. So it's a good idea if you're asked, right, to write down that y-intercept is none. That way we know that you've checked it and that you recognize that fact, not that you just forgot to do it or didn't know what to do with it. This is actually pretty cool. The 2 points that we have are enough. We don't even have to have any extra points to do this graph. So Tyler, if you thought the first one was weird, this one's weirder.
Yeah, I don't like this.
Okay, so we have to get close to the lines, right? And we have to be on the left-hand side. So if I'm on the left-hand side and I'm getting close to my dotted lines, the only way to do that is to look like this. Okay? And the same weird thing, so to speak, is going to happen on the right-hand side of the graph. I need to be trapped between these dotted lines, but get close to them. So it's going to look like that. And if we didn't have enough points, of course, we would test an additional point to find one that would work for giving us some more information. Okay, shifting gears slightly, we're going to do the other part of the directions or the other part of the title of this section. It was rational equations and inequalities. So we've done the equations part, now we're going to do the inequalities part. This one's really nice because it has a 0 on one side. So this is where we're going to start. We're going to solve the following: x plus 3 divided by x squared minus 1, and it's greater than or equal to 0. Okay, the first thing to do, if it's not already done, is to make sure you've got 0 on one side and everything else on the other side. So that step's done for us. We'll do another one in a minute where it's not, and we'll start back at that point. But that's already done for us. After that, we're going to factor everything, much like we have done when we did asymptotes, right? Looking at factoring and reducing. So we're going to attempt to factor what's here. The x plus 3, that doesn't factor. We don't have to worry about that. That's done. But the denominator factors, and in fact, we just saw it a minute ago as x minus 1, x plus 1. right? Okay, so that's nothing new so far. You know how to factor those. The next thing we're going to do is we're going to get test points. So the way that we get test points is that we set each factor equal to 0, okay? Not because that gives us the answer to the equation, it's just a part of the process. So we're going to set x plus 3 equal to 0, x minus 1 equal to 0, and x plus 1 equal to 0. So tell me what our test points values are. X equal what? -3, 1, and -1. Okay? Now, we've done what I'm about to do before. We did it with polynomials, and it works exactly the same with rational equations. In this case, sorry, inequalities. We're going to put them on a number line. They don't really have to have sort of, the right perspective on the number lines. You don't really care where you put them. You just need to make sure that they're in order. All right, so obviously -3 would be first, and then -1, and then 1. So you're just putting them in order on a number line. Now, there are some of these values that you absolutely can't actually let this be. In particular, think about your denominator. There are some values that would make this denominator equal to 0. What are they? Plus and minus 1, right? So if you think about this in terms of a number line, I can't really equal this one or this one. It's not allowed. Would it be okay to have a 0 in the numerator? Sure. So if you're thinking in terms of open circles, closed circles, you could actually put like a closed circle on the 3 if you wanted to, just to give yourself some perspective to say, yep, I've tested this and it works. Oh, that was really a big dot. Okay, so this is sort of a reminder to us. It will help us with parentheses and brackets at the end, okay? What I need to do then is I need to test a value in each part of those intervals, okay? So we need to test values. There's absolutely nothing that says what value you need to test. It just needs to be in that interval. So for instance, if I choose to test -10 and Deja chooses to test -4, we won't get the same answer, but we will get the same sign. And the sign is what I care about. So we pick any value in those intervals. I usually do try to pick values that are convenient or as small as possible just because they're usually easier to work with. So I think -4 is probably a good choice here, just in terms of convenience. What would you like to test between -3 and -1? -2. That's a convenient value. How about between -1 and 1? 0. It's the best value to test ever. If you ever have an opportunity to test 0, by all means, test it. And I need a value bigger than 1. 2. Okay, so again, if you chose different values, it's not going to hurt anything. What I need for you to do is to plug in those numbers into the original expression that was set equal or greater than or equal to, in this case, 0. And what I care about is, do I get a positive or do I get a negative? That's what I care about. So let's check it out. If you plugged in -4, will you get a positive or will you get a negative? You might be able to do it in your head. You might want to grab a calculator or pencil. You get a negative. You're right, Nee. You get a negative on that one. Try -2 now. If you plug in -2, positive or negative? It's a positive. You know what? I'm going to use a different color because this is really running into things. Okay, how about plugging in the number 0? We can all do that one in our head. What happens when we plug in 0? -3, because this gives me the 3, gives me the -1, so that's -3, it's a negative. And what happens when I plug in 2? You get a positive. I want you to notice that they alternated, but I don't want you to think that that always happens. It doesn't always happen, so please be careful to check them. A lot of times it will, but not always. Which ones are our answer? The positives or the negatives? How do you know, Andre? Because of the inequality sign. The inequality sign said greater than or equal to 0, and greater than 0 are positive numbers. So my solutions to this are the positive parts right here. Parts that I just shaded. That shading is so light. So we need an interval now to represent the parts that are positive here. And that's where those dots and circles and opens and closed and everything are useful to us as a reminder. Am I allowed to equal -3? Yes. So I will equal -3, and I do that with a parenthesis or a bracket. I do that with a bracket and a comma. And then I'm moving from the left to the right, and I get to the value -1. After the -1, will I use a parenthesis or a bracket? It's a parenthesis because there's an open circle, because that would make the denominator 0. And then I'm doing a union. I need to skip the next interval because it was negative, right? So if I'm moving again from left to right and I skip the interval from -1 to 1, I pick back up at the number 1. Do I pick back up with a parenthesis or a bracket? A parenthesis. And then what do? I put an infinity, and infinities always have a parenthesis. So this would be my interval. Sometimes parentheses, sometimes brackets. All right, one more example. You ready? Okay, I already told you this was coming, right? There's a 3 on the right-hand side. If you try to factor and you try to do everything we did and forget about that 3, you will not get the right answer. It's not going to work. You can't do anything with the test points. You can't do anything we did if the number on the right-hand side is not a 0. So what would we do first to make it a 0? We would subtract it, exactly. So we've got a little bit of work to do before we're ready, if you will, to actually find any test points on this one. I need to do this. It needs to be subtracted to the left-hand side. Now again, that's not in a form that's like the last one, and I need it to be in that form. I need it to be a single fraction. How am I going to do that? We need the common denominators, right? I'm going to move my 3 up a little bit just to remind you this is the same as 3/1, right? So I need these to be combined, and in order to combine a fraction and an integer, I will have to get common denominators to do that. What would the common denominator be? The one that's there, x minus 2. Yeah, because there's only one of them. So I need to multiply the numerator and the denominator by x minus 2. All right, so mine's kind of a mess at this point. I'm going to clean it up just a little bit. This is x plus 1, and then it's minus 3 times x minus 2. And they're all over the common denominator now, x minus 2. What do you suppose the next thing is we do? Combine the like terms on the top, simplify, distribute, and all that good stuff. So if I distribute first, I have x plus 1 minus 3x plus 6. Remember to distribute the negative. And then tell me what we get when we actually combine the terms now at this point. Negative 2x plus 7. And will that factor? No. Could it factor at this point? It could. I mean, after combining those things, we could get something to factor and simplify, reduce. I mean, like, that's totally a possibility. So do check that. But on this one, it doesn't, because there's nothing in common with the negative 2x and 7. All of that work is where this last problem started. Okay? So if there's not a 0 on the right-hand side, there's no doubt that there's more work involved. So what did I actually do after I had the 0 on this side? Well, I factored, and we already said this one didn't factor on our example over here, right? There's no factoring for this. It's in factored form. What did I do after I factored? I set each factor equal to 0. I looked for test points. Okay, so we're going to do our test points next. So the test points are taken by taking each of the factors, in this case that's the whole numerator and the whole denominator, and setting them equal to 0. So I have negative 2x plus 7 equals 0, and I have x minus 2 equals 0. This first one's a little bit messy just because I am going to get a fraction, but I have negative 2x equals negative 7. It's okay to leave it in fractional form, but I think probably for the purposes of putting it on the number line and everything, probably writing it as a decimal might be more easy to think about. More easy is terrible English right there. Don't do that. Easier to think about. What would you get if you divide negative 7 divided by negative 2? Sorry, I didn't finish my 2. 3.5. Okay, cool. How about the other one? What does x equal for my other test point situation? 2. I have 2 and 3.5. After that, I have my number line. Which one comes first? 2 will, because they're both positive, yeah. And then 3.5. Okay, we need points in the intervals to test. What is a point before 2 that you might want to test? 0 is my favorite. You could test anything else you'd like, but I like 0. How about between 2 and 3.5? I would test 3 as well. And then after 3.5, maybe 4. Okay. And we're going to test each of these. And the question should be in your mind, well, where do I test them? Do I test them here or do I test them here? So what do you think?
Bottom.
Original is what we normally do, but this one's actually going to be on the bottom. Unfortunately, if we've made mistakes in the simplifying, we're kind of out of luck at that point. But the reason we need to test it on the bottom one is because what we're testing is whether things are positive or negative. And the only way that that's going to work is by looking at what we've set equal to 0, or in this case, greater than 0. So we didn't actually talk about this, so let's pause for a second and do this. Obviously, x equals 2 is not allowed because it's in the denominator. It would make the denominator 0. So I have an open circle on x equal to 2. What's going to happen at 3.5, though?
Just make the numerator 0.
It makes the numerator 0, and that's okay. I can make the numerator 0. That's not a problem. But this does not say greater than or equal to 0, does it? The last one did. This says just greater than 0. So if the numerator is equal to 0 and the whole fraction is 0, does that actually work for it to be greater than 0? It doesn't in this case. So even though it's okay to let the numerator be 0, it doesn't answer the question that this question asks us, right? Because it says greater than 0. So I have open circles on both of them in this case. Let's test the points now. Into the reduced one that we have, the bottom and the bottom left-hand corner. Plugging in 0. What happens when I plug in 0? That's friendly. Positive or negative? Negative, because I have 7 divided by negative 2. It's a negative. All right, what happens when you plug in 3? You might want to grab a calculator or pencil to do that one. Do you get a positive? Or are you just guessing, Rebecca? You got a positive. Yeah? You should. So that's good. Yeah, that's right. And then we need to plug in 4. What happens if you plug in 4? Nee says negative, and she's also right. It's negative. So like I told you, often they will alternate, but they do not have to. So don't think that that's an always thing and you can just fill it all in at will, okay? Which part of this is our answer, the positives or the negatives? Positives. Is the positives always our answer? It wouldn't necessarily be. It's because this particular problem says greater than 0, right? That's the reason that positives are our answer. So what does this interval look like for our answer? Parenthesis or bracket? Parenthesis, what's the next value? 2. Yes, it is. This is my solution for this one. So I don't end up actually having anything going to infinities on this case.